Hope you enjoyed the Banana Farm tour on Lecture 2B. And now to complete our journey into super efficient buildings, let's finish with this third section focusing on passive techniques, cooling equipment, emerging radiant methods that may even eliminate electricity for air conditioning, efficient building equipment, and how efficient buildings create important forms of value beyond just saving energy. Let's start with how to design buildings so they keep you comfortable without using any energy. Passive design, described in this classic text, can keep you cool as well as warm. Smart people have done that for millennia, from China, India, Rome, Persia, Arabia, to the American Southwest, as these two histories richly illustrate. My own house simply updates 6,000-year-old North Chinese passive solar architecture, where Neolithic villagers faced their homes' sole opening towards the equator to catch the low winter sun and trap it in indoor thermal mass, while an overhanging thatched roof blocked the sun that was high up in the summer. And probably they augmented by summer cross ventilation. About 4,000 years ago, Chinese scholars carefully studied solar motions and started laying out all towns' main streets east-west so the houses could face south. Even Beijing shows this influence today. Facing south is a deep-seated cultural norm. The emperor would hold audiences facing south to symbolize brightness and enlightenment. Again, many diverse cultures have long mastered similar methods until they were often lately forgotten. High deserts are a nice example. They're blazing hot in the summer, but sub-freezing much of the winter. And yet, more than 1,200 years ago, up to 1,000 people, apparently of Asian heritage, lived in this 4-story Anasazi settlement of Pueblo Bonito, whose interior temperature varied less than a third as much as the exterior temperature, even though it had no windows, just holes in the thick walls. Some ancient cliff dwellings, like those at the lower right, built under overhangs to maintain even tighter temperature bands, and they did even better. An underused desert resource is its clear access to the sky, especially at night. The radiant temperature of clear sky is about minus 40 degrees. So the ancient Persians made sorbet for the Shah by putting a dish of water at the bottom of a well so it could radiate up to the sky, but the sun couldn't shine in. The water would reliably freeze overnight, even in the hot desert. When Professor Takeo Saito taught at Tohoku University, he used selective compound parabolic solar decollectors to reject heat to the sky year-round. And he got at most 15 Celsius daytime and under 10 Celsius night temperatures right through the summer. It's a Houston-like climate. Even in the humid Kansai climate like that, he could cool all but the lowest temperature supermarket food cases purely passively using no compressors. And now US researchers are testing even more efficient far infrared radiative surfaces for passive cooling. A little more on that later. For tropical apartments like those sprouting all over urban India and southern China, air conditioning is adding huge electric loads that drive more coal-fired generation. Of course, the air conditioners can get a lot better and smarter. That's part of the SEED, S-E-A-D program at superefficient.org to move about 15 firms around the world to bring best practice to the 3/4 of home appliances they make that have not yet been built or bought, and then finance any extra cost on bill like India's LED lamps. But at least as important is to adapt and adopt the best design methods that can save 90 or 100% of the needed cooling. For example, these mid-rise apartments, which were proven popular in the Indian monsoon by architect Diro Thadani, use passive convectively vented double walls and super efficient ceiling fans to keep you feeling about 16 to 19 Celsius degrees cooler with just 2% higher construction cost. So that's about 11 or 12 Celsius degrees of increased comfort range from the passive features, plus another 5 to 7 from the fans. Such comfort sensation numbers, by the way, come from experiments where people experiencing various thermal conditions are asked how comfortable they feel in a rigorous way that's backed by physical and physiological measurements. With a few further refinements to these apartments, better sashes, glazings, and so on, they could deliver decent comfort with probably no air conditioning. These designs were very popular because the gap between the walls left ample storage space, and the inner wall always stayed dry and mold-free right through the monsoon. By the way, you may wonder, how do the fans give you such a big increase in comfort range? Well, normally it'd be a 5-degree range if you take account of the fact that the airflow is turbulent, not laminar. ASHRAE doesn't do that. They assume 3 degrees. And the 5 degrees then become 7 degrees with the whoosh feature of the Haiku brand of fans from a maker called Big Ass Fans, whose logo is the back end of a donkey. And if you press the whoosh button on the control, we have this in RMI's Innovation Center, then the fan motor speed fluctuates, little torque jitters to oscillate the air velocity at, I think, 0.42 hertz. And this change in the air velocity emulates the coevolution of your skin neurons with the frequency spectrum of natural wind gusts, and it raises your cooling sensation by about 2/5. This was discovered in Japan, and they're starting to use it now in cooling cars. Now, that is shown here, just in case you want to know what it looks like, just a beautiful little sculpture. This old visitor center that we helped design in the southwest high desert of the US, where it regularly gets to 40 Celsius, uses Persian draft towers, and trom walls. That's a masonry wall with a glazing over it, heating the air in between and helping the wall retain solar heat. Other passive features, altogether, they save 30% of the electricity and construction cost. A Persian draft tower is a chimney you see in the upper middle containing a little water mister near the top. So the evaporating water mist cools the air and causes a steady, cool downdraft with no fan, which the deer in the upper left is enjoying. The total energy savings were 70%, by the way, with no extra cost, including 96% savings on cooling and 92% on fans. I just revisited this building and it's still working fine. Now, Stanford has the Carnegie Department of Global Ecology with a wet lab workshop and office that uses only 53% the usual amount of electricity compared with strict California code, and it emits 28% of the usual CO2, yet had normal construction cost, and it has exceptional occupant satisfaction. Except for under 200 hours a year, it's non-refrigeratively cooled and gets 50 units of cooling per unit of electricity. That's about 10 times normal refrigerative efficiencies. And it would have been not 50, but 100 times or more productive of cooling than it used electricity if Peter Rumsey had been allowed to design the pumping system too. Now, how does he do that? As in the previous project, a Persian draft tower drops 15°C air into the space without fans. And then in addition, a night spray on the roof radiatively and evaporatively cools water to 10 Celsius degrees for storage in a tank that circulates to a radiant floor slab and a fan coil. And then used air from the lab feeds the fume hoods. Passive buildings can be big. Zimbabwe's largest office and shopping complex, the 1996 Eastgate Center in Harare, uses passive design inspired by turbine mounds, which use very sophisticated air oscillations and passive controls to hold temperatures within a very narrow band required by the fungi that the termites farm. Now, this building uses 90% less mechanical energy to deliver normal comfort, if not better, to over 31,000 square meters with normal construction cost and 20% lower rents. Passive ventilation is millennia old. The ancient Romans had passively air-conditioned cities with stone air channels. The 1871 old executive office building next to the White House had a brilliantly designed passive cooling and ventilation system driven by convective heating in 6 solar heated domes that were supplemented by steam pipes on cloudy days. You see the inside of one of the domes on the left. And their convective suction pulled in outside air through slots under the windows. The air would passively cool inside that meter of granite and drop out condensate on its way through the walls. And then the cool air would waft across your office, up a shaft or out the transom over the door, down the hall, and then up to exit out the dome vents. Over decades, the purpose of these components was forgotten. The air shafts got blocked, the domes were painted black for wartime blackout, and 782 noisy, inefficient window air conditioners plus some bigger units were installed. So one aim of our 1994 greening of the White House was to gradually return the building to original design intent so the occupants doing the nation's business are not always distracted by noise and discomfort. In the new offices of the British Parliament, computational fluid dynamics provides excellent and completely passive ventilation. Those things that look like combustion chimneys or convection chimneys. Back in 1994, that building's designer, Alan Short, who's now professor of architecture at Cambridge, had saved half the energy and $1.4 million of capital cost net by passively cooling and ventilating this 2,000 person lecture and lab building in the north of England, making it one of the cheapest university labs ever built. Internal heat gains as high as 75 watts a square meter are passively removed by convective airflows of 2 to 6 cubic meters per second through decorative chimneys. The greater the heat, the stronger the convection. Likewise, air enters the auditorium through planta under the raised seating and therefore convectively cools people directly. Engineering students read about chillers and fans in a building that has no chillers and fans to show them. The campus's chief engineer said that in the very hot summer of 1995, of all the university's 250,000 square meters of buildings, this one with no chillers offered the best refuge from the heat. And one of the world's most efficient buildings on Hawaii's Big Island combines a passive solar chimney with seawater heat exchange to do all the cooling and all the ventilation. Before we leave passive cooling, let me report an important innovation just published by Professor Forrest Megger's team at Princeton about a year ago. Other things being equal, air movement, humidity, clothing, and metabolic rate, your comfort sensation depends about equally on the dry bulb air temperature and the mean radiant temperature, the average temperature of the surrounding surfaces that radiate infrared to or from your body. And yet no one had studied indoor conditions in which mean radiant temperature was over 4 Celsius degrees below the outdoor air temperatures of over 28 degrees. So the Princeton team did that. They went further and they cheekily demonstrated effective radiant cooling outdoors in Singapore in January, keeping people comfortable in tropical conditions, upwards of 30 Celsius, 67% relative humidity, nearly still air, and yet without drying or cooling or moving the air. Instead, they cooled people purely radiatively by absorbing far infrared radiation from their bodies into vertical metal panels that subtended a big solid angle and were cooled by a dense capillary mat circulating slightly cooled water. The back of that panel, the outside, is insulated and painted white to reduce solar heating. To prevent convection to and condensation from ambient air inside the space, the front of the panel is shielded by an air gap 50 micron polyethylene film that's transparent to 82% of the infrared that your body radiates. People inside the 10 square meter walk-in pavilion, think of a bus stop shelter plus foyers, they confirmed that they felt comfortable using classical comfort theory measurements. And as the extended psychrometric chart shows, mean radiant temperatures around 23 to 25 Celsius can deliver thermal comfort up to at least 32 C, that's 90 F, ambient temperature at 80% relative humidity. Of course, radiative cooling, typically from ceilings or beams, is getting common in today's most efficient buildings. But previously, it had been thought to need tight control of indoor humidity to prevent condensation. Instead, this demonstration shows that you need only keep humid away from cool, and a few microns of plastic film can do that. Air handling in a radiatively cooled indoor space can then depend just on ventilation and health, not on cooling. That allows a lot less airflow, energy use, noise, and cost. More on this later. Now, if you do need to move air, but you can't do it passively, here's some basic physics to bear in mind. The power used by a fan is the product of its flow times the pressure head it works into, the friction it must overcome, all divided in green by the product of the efficiencies of the fan and the motor. Notice that the fan and motor systems together typically offer about 2 or 3-fold efficiency gains. I need to update that number. As you'll see later, the fans are better now. Let's see. Sometimes more, but of course you should do those things, but reducing flow and pressure drop often offer much larger opportunities, worth at least 5 to 10-fold. And you should do all of the above. Which come first? Reduce the flow first, then reduce the pressure drop, because both of those will make the fan and the drive system smaller, therefore cheaper, helping to pay any extra costs of making it super efficient as well. Ways to need less airflow include making the building more thermally efficient, or its equipment more efficient, so you needn't deliver as much hot or cold air. Better still, provide comfort radiatively or otherwise without heating or cooling air, since air is a poor heat transfer medium. Eliminate toxic materials from construction and maintenance so the air always stays clean. Enforce non-smoking rules and deliver fresh air in the most effective way. Combine all of these and your air handling equipment will get even smaller and cheaper. Peter Rubsey offers 3 lovely illustrations of why it's better to deliver heating or cooling via water than via air. First, a 1-inch tube with a 1/10 of a horsepower pump delivers the same heating or cooling flux as a 20-inch duct driven by a 3/4 horsepower fan. How much is 3/4 of a horsepower? Well, just visualize a medium-sized horse working hard and never resting. Ease the task and earn good horse karma. Here's a visual version of that story with slightly different numbers, which depend on the temperature difference. And in case you forget that water has over 3,000 times the heat capacity of dry air per unit volume, here's a little visual reminder. Just remember the sight of these 2 big bags of air compared to that tiny cup of water that has the same heat capacity as all that air. Even more basic than fan efficiency is the strategy of how do we distribute fresh air in a building. The standard method is to blow fresh, cool air, or maybe not so fresh, down from the ceiling. That's called turbulent induction, and it mixes the relatively clean supply air with the dirtier air that's already in the room. And therefore, any fumes, germs, CO2, and so on all get mixed into the air you breathe, as shown on the left. That is unhealthful, noisy, inefficient. Wouldn't it make more sense, as on the right, to supply clean air at or near floor level and let it gently push the dirty air out at the top so you're breathing only clean air all the time? And wouldn't that make even more sense if your building isn't all passive or radiatively cooled, so you're having to supply moderately cool air, which rises as it warms? This is the principle called displacement ventilation. And to examine how the choice of air distribution method affects our health, the late engineer Malcolm Lewis did this simulation a few decades ago, long before COVID-19, but obviously far more relevant now. Here's his layout of a fairly typical office with air distributed from above by turbulent induction. The little yellow biohazard symbol shows where an infected worker is about to sneeze. And the red represents the sneeze, and its infectious aerosol quickly spreads across half the office. Lots of people having to stay home. Now, in contrast, if fresh air is diffused from low down, even from one corner of the office, like this unimpressive design, the aerosol is quickly carried up and out before it can spread and sicken other workers. Of course, best practice is also to supply 100% outside air. There's the sneeze, but nobody else gets to breathe it. 100% outside air rather than mixing that clean air with dirty air recycled from the exhaust, as most old buildings still do. Displacement ventilation is usually supplied either at baseboard level or through floor-mounted grills or diffusers, so the air gets distributed from a shallow underfloor plenum. That needs no ducts under the floor or above a drop ceiling, and that greatly reduces construction cost and time and pressure drop. The total static head the fan needs to overcome drops below 250 Pascal, which is 1-inch water gauge, so the fans and chillers get smaller and cheaper. The air gets supplied at 18 degrees Celsius, not the traditional 13, because the colder air is no longer needed. So the chiller and all the pumps and fans and stuff that run it need less energy and become more efficient. And yet that less cold air cools you more efficiently because a little chimney-like convective airflow rises up along your body, helping move the air and take away the heat. Any heat from computers on the desk or lights higher up also goes straight up and out without heating the people. Fan noise disappears. Less airflow properly distributed delivers better air quality, better health. And without the costly drop ceiling, whose only remaining function is to hide sprinklers, the floor-to-floor distance shrinks, or the ceilings can get higher for better daylight distribution. The space can be quickly and easily reconfigured. If you need to move people around, the power or signal wires in the underfloor plenum are easily moved if necessary. You just pop up a carpet tile and a floor tile, but you don't need to move ducts or wires or overhead lights because the whole space is suffused with glare-free natural light and indirect supplementary light. So the tenant saves tens of dollars per square meter and year on the costs of reconfiguring the space. That's a big deal. And the developer's total capital cost is comparable or lower to normal. Construction can be 6 months faster. So we integrated all those pieces with 2 major firms, and this approach is spreading very nicely. Displacement ventilation is perhaps most valuable in hospitals, especially operating rooms. 2 to 4% of US surgical sites get infected, about a third of them through airborne contaminants. 3% of infected patients die. 2009, that was 13,000 deaths in the US. Treating their infections also cost over $7 billion a year, for which hospitals don't get reimbursed. Of course, operating theaters need laminar flow using cleanroom technology. Don't they already do that? Well, surgeons and hospital engineers tell me it's common only for orthopedic and other implant operating rooms where infection risk is especially high, but not generally in many others. You see, operating rooms lack the airborne contaminant control standards used in clean rooms, and many ORs have ceiling obstructions that add turbulence. Now, meanwhile, the Centers for Disease Control and Prevention keep raising their guidelines for air changes per hour in the room, and that breaks hospital space constraints and financial budgets. And yet, a pathogen in the air has the same physics as a dust particle or a toxic molecule in the air. Well, our semiconductor and chemical industry partners routinely use smarter aerodynamics to achieve better contaminant control with less airflow. It seems time to get those experts in the same room with CDC's experts and ask them how their infection control outcomes are rationally linked to airflow guidelines. I doubt they are. And then learn from other industries' best practice. This could probably save thousands of lives a year, billions of dollars a year, and untold capital cost for new healthcare facilities and electricity systems to power them. Now let's take a few minutes to tour some of the several-fold efficiency gains available in today's common packaged HVAC equipment. It's simple to save a lot of energy in the often dreadful equipment widely used to condition commercial buildings, especially the so-called rooftop units, the big boxes that condition over half of US commercial floor space. In a typical convenience store retrofit in hot Davis, California, 50% energy savings paid back in less than a year from adding an evaporative pre-cooler, a controller, and a little plastic tubing. The compressor shrank by a third, great economics. And the best units that DOE elicited in an advanced rooftop unit campaign are nearly twice as efficient as the ASHRAE 2016 90.1 standard. So their full use in the common, say, 10 and 20 ton sizes could save about $1 billion a year in US commercial buildings. Now, just improving the components of a simple rooftop chiller using 2003 technology, about 20 years old, could raise the savings to 80 or 90% in relatively dry climates. What are we waiting for? And putting together even more good stuff in a standard rooftop box could do even better. That was prototyped 24 years ago. In fact, it could be further improved with a direct drive axial fan rather than the belt-driven fan you see there, and with added evaporative and desiccant modules. Today's best units actually have an integrated efficiency metric, which is now called IEER, upwards of 21, but two-stage evap has demonstrated 26 to 56, and regular maintenance is essential too. As with much equipment, a bad unit, well maintained, will often outperform a good unit, badly maintained. What about the giant water-cooled centrifugal chiller systems used to air condition most big commercial buildings? Well, the chiller, shown in a colored box here, lies at the heart of a 5-loop process. Reading from left to right, the way you would design the savings, unwanted heat in the space warms circulated cool air. That heats up water in a coil. That water evaporates the refrigerant that's then compressed, transferring heat in a heat engine cycle into condenser water, where it's exchanged into warm water that's cooled by evaporation into outside air in a cooling tower. So the heat is indirectly transferred through heat exchangers and a compressor cycle from inside air to outside air. And the cool throughwant flows from right to left, opposites of the design process, which should flow from left to right. And there are 4 devices here using power, a fan at each end, 2 pumps, and the chiller. The supply fan and chilled water pump heat ends up as extra parasitic chiller loads, making the chiller even bigger and using even more energy. Oh, by the way, is anybody wondering why the US unit of refrigeration is called a ton? It's the cooling done by melting 1 short ton, 2,000 pounds of ice. Because before Mr. Carrier's refrigeration machine, we bought ice by the ton from horse cart vendors who would saw it out of frozen northern lakes, ship it to the cities, and store it under insulating straw or sawdust. So the number comes from the latent heat of fusion of water, 80 calories per gram. Now, the Singapore wizard Lee Eng-lok and his protege Peter Rumsey routinely triple the efficiency of big new water-cooled centrifugal systems, shifting design power intensity, that is kilowatts per ton, for each major component from the second column to the third column, and by means explained on the right in the how column. And the total capital cost goes down, comfort and reliability go up. Now, exceptionally, let me do this chart in barbaric units. I will add it in metric in the PDF right after this slide. Mr. Lee rigorously designs out duct and piping friction. So the supply fan has only about 1.3 to 3 inches water gauge of total static head. And you can do less, even an inch or less, with underfloor displacement ventilation. The chilled and the condenser water loops similarly have heads of only 20 odd feet. Now here, Mr. Lee used some British variable speed vane axial fans and typically German pumps, no primary secondary pumping, which is a sign of excessive piping friction. So these improvements together would cut the fluid handling parasitic loads by an order of magnitude. Notice the 0.6 supply fan versus 0.06, and similarly below. Now the chillers have optimized impeller speed in their compressor. That doesn't cost extra. One gear ratio costs the same as another. You just need to specify it properly. And he uses very close approach temperatures, often around 1 Fahrenheit degree, because copper is cheaper than kilowatt hours. His cooling towers, typically Japanese Shinwa, save 90% of their energy by being specified big, squat, and fat, with big, slow fans rather than small, fast fans. Again, basic physics. And of course, all the cooling towers are dispatched in parallel at variable speed. So all this adds up to 0.588 kilowatts per ton at the Singapore design hour, or down to the bottom, 0.52 if you use 2 separately optimized cooling coils at 4.5 Celsius for condensing, that is for drying the air, and 12 for sensible cooling. So all that raises the total energy saving to 70% from supposedly good normal practice at lower capital cost with better comfort. This practice spreads slowly to engineers whose fee is a percentage traditionally of the cost of the equipment they specify. Now, here's the same in metric units. If you do nonetheless have a big water-cooled centrifugal chiller system, here's how Mr. Lee does that. And COP is the amount of cooling you get per unit of electricity. So his end-to-end supply fan through cooling tower system COP at the Singapore design hour, one of the world's toughest climates, is 6.8 with or 6 without the dual chilled water temperature. So notice again the order of magnitude savings in the supply fan, the pumping loops, both of them, and the cooling tower by redesigning components, including pipes and ducts, to minimize friction and optimize performance. Now, there is one trick in Mr. Lee's whole system design, and that's rethinking the cooling coils by correcting a 1921 misinterpretation that Willis Carrier made in his lab data. Mr. Carrier thought that airflow through a cooling coil was turbulent and water condensed in a film. But the late engineering professor Sam Luxton in Adelaide found experimentally, look at the photos on the right, that actually the airflow is laminar and the condensation is dropwise. So if you take the usual deep, dense cooling coil at the upper left and turn it around sideways to make a shallow, sparse coil at the lower left, and then you blow the air through it slowly, less than a meter per second, less than 200 feet per minute. That's a quarter of the normal face velocity. Then you preserve those precious droplets and their extra surface area. And that increases dehumidification 29% per unit of sensible cooling. It cuts the airside pressure drop that the fan power has to fight by 95%, a factor 20, and it shrinks the evaporator load on the chiller, and it shrinks the entire cooling system. I understand Carrier Corporation has long had such coils in the lab with production intent, and I'm eager to see them in the market. Of course, if you used radiant cooling, you wouldn't need the coils or the fans. Now let's pursue that one a bit. In April 2021, I asked Mr. Lee how much better he could do than these 2-decade-old numbers I've been showing you. Was there anything new besides some better Danish supply fans that could say 0.03 kilowatts per ton? Well, yes, there are actually. Some Singapore buildings now simply pump the chilled water a bit higher, hardly adding pumping head because it's a low friction closed loop, just a bit of gravity you pay for. And then they let the cool air made from that chilled water flow downward convectively through the building rather than blowing it around in fans. You could also eliminate the cooling tower fans as we used to in the old days by using old-fashioned taller towers that run convectively. and that incurs a slight extra pumping head. And then the chiller could drop to 0.33 kilowatt per ton. Look at that red number in the middle of the chart, using optimal 10-degree coils. So Mr. Lee's red markup improved that 3x efficiency gain he already got 20 years ago to as much as 5x. Okay, well, what's next? First, about half the remaining cooling system power could be saved by underfloor displacement ventilation, as we saw earlier, plus a passive latent heat exchanger. What's that? Well, dry climate buildings like RMI's Innovation Center in Colorado use a heat exchanger to recover 93% of the sensible heat, and therefore they preheat, or perhaps in the summer pre-cool, the outside air coming in from the exhaust air going out. But if you're air conditioning a big building that needs the humid outside air to be dehumidified as it enters, isn't it wasteful to discharge stale but still relatively dry air from the building and waste its dryness, its lack of latent heat? Well, yeah, it's really wasteful. So Mr. Lee figured out a passive latent heat exchanger that could be assembled from off-the-shelf components to recover that dryness passively. And here's how it works. You take the moist outside air drawn into the building and pre-cool it. I'll tell you how in a minute. Capture the condensate that drops out when you cool it. Run that water, that condensate, preferably by gravity, to the place where you're discharging exhaust air from the building. Evaporate that water into the dry exhaust air. This will cause evaporative cooling because the conditioned exhaust air is drier than the humid ambient air outside. Now you capture that evaporative cooling in a heat exchanger, move it back to where you started, preferably by a heat pipe passively, and use it to cool the outside air. Any engineers in the house are welcome to do the calcs. This practice remains rare, but it's useful and it's not that hard. Okay, even more radically, add the magenta type. Radiant cool delivery, like we saw in the Singapore experiment, plus passive radiant heat rejection, with special surfaces that reject the heat to the night sky, even the day sky, even the cloudy sky. Even if you needed an efficient mini pump circulating cool water to radiant panels rather than coupling everything with heat pipes, you could probably still cut the total cooling power of the whole system to roughly 1/1000th of standard practice, with much lower capital cost. Or if the radiant cooling panel inside the passive radiator outside, and the passive radiator outside are passively connected, so you don't need the little pump, then the electricity used is zero. Let's try it. What are we waiting for? So what do all these examples teach? Start with the end use effect you intend. Optimize buildings as whole systems, not as a bunch of components. So the key to cutting construction costs is often to use expensive windows. In particular, pay for the efficiency, largely or wholly or more, through the mechanical shrinkage it causes. Cut the most capital cost by saving from downstream to upstream, as I'll describe later, and optimize the sequence and timing of design steps. Do the right steps in the right order. And to relieve any anxiety by design professionals about getting paid less for specifying smaller mechanical equipment, let me reemphasize that RMI's Innovation Center came in under budget slightly early with no mechanicals, but happy designers. Because we adopted integrated project delivery, we think for the first time in a small building. And under this contractual arrangement I mentioned briefly earlier, the design team, the owner, and the builder are all predictably rewarded for common success and predictably penalized for common failure. All the incentives are fully meshed and aligned, so there's no finger pointing. The designers could earn even more by outperforming. So it has the effect of performance-based design fees, but also it importantly aligns everyone's incentives and greatly streamlines processes. What performance metrics and targets should an owner or financier seek from her designers? Well, this chart summarizes technical efficiency benchmarks in metric for big new office buildings in a semi-tropical climate. The measured results from Rohan Parikh's Infosys offices in India are in red on the right. Before that, in green, is RMI's Innovation Center in 2018. Then in blue, or in aqua, the best contemporaneous Japanese practice, and in white, the best US practice. Farther to the left are two levels of common practice called better and normal, found in over 90% of US buildings. You see a retrofit opportunity? Most of the buildings are in the normal column. So best US practice in the right-hand column in white cuts total and electrical needs, the first two rows, by 5 to 10-fold. The as-used lighting power density by 5 to 24-fold in the third row, plug loads by even more. Glazings insulate better by an order of magnitude. They become almost perfectly selective in sorting light from heat. Add super insulation, which isn't even shown here, and a heat rejecting roof, and you need 3 to 5 times less cooling per square meter. Then you can make the cooling system about 4 to 13 times more efficient, or just get rid of it. Mechanical savings help reduce capital costs by several percent and use the floor space about 1 to 6 percentage points more efficiently. Whatever exists is possible, and efficiency is a business opportunity. Rinse and repeat. Better technology is important too. As insurance against inefficient buildings, in 2018, RMI organized powerful partners to establish a global cooling prize for affordable and at least quadrupled efficiency window air conditioners. These small and generally very inefficient units, now over 8 billion of them, are expected to quadruple by 2050, adding a half Kelvin or more of global warming by the end of this century, and straining power supplies and capital budgets. So this open contest was led by former RMI Managing Director Ian Campbell, previously CEO of York International's Americas division, one of the top global players in air conditioners. The conditions were challenging. Over 2,000 registrants were winnowed down to 8 finalists whose prototypes are completing, may have completed by now, lab and field tests in India. And the winner, announced in spring 2021, got up to $3 million of prize money. I think it actually was in April. That was to scale up production. The finalists were from China, India, Japan, US, UK. The winners were actually 2 leading makers of air conditioners whose test units achieved not just 5x, but about 10x reductions in climate impact. And those 2 firms have a combined world market share around 25%. So we're already starting on the path to global scaling. Wow. Sweat the small stuff too. If your house, for example, is heated by circulating hot water from a furnace, you probably don't think much about the little pump that overcomes a typical 1 or 2 watt frictional head in the piping and the radiators. But scientists at the Technical University of Denmark in Nürnberg found in 2007 that Europe has 120 million of those pumps. They're 5 or 10 times bigger and 4 to 8 times less efficient than they should be. Many of them run continuously, and they use about 15% of the home's annual electricity. So if you make all those little pumps properly efficient, right-sized, a lot smaller, and self-controlling, Europe could save the continuous output of 8.5 gigawatts of power plants, emitting 50 megatons of carbon a year, or 1/6 of Europe's Kyoto obligation. Circulator pumps last about 13 years, so if we had begun replacing them when that analysis was published, we'd be all done by last year. Next, let's examine 3 examples of super efficient household equipment and integrative design that can help switch buildings from natural gas to very efficient electrification, not just any old stuff off the commodity list. There are many ways to make domestic hot water, but of course we should first ask how to use it more efficiently, and most of it can be saved. And yet the second biggest US household energy use is poorly understood. We didn't know in 1991, for example, The whether, and we may still not know whether when you're taking a shower and the hot water gets cooler as it starts to run out, you're likely to increase the hot flow or reduce the cold flow. Nobody'd measured it. It wasn't even clear if you set the aquastat on your electric water heater to supply a certain temperature, whether it would actually do that. That temperature may well be 13 to 16 Celsius hotter than it needs to be, depending largely on whether you use enzymatic detergents to wash dishes and clothes and how you assess the risks of infection by Legionella bacteria. So anyway, untangling many such detailed required a 400-page book, 412-page book. Water heating seemed at first to be simple and mundane, but it turned out to be the most complex end use of all 6 we analyzed, each at book length, 1 per year from 1986 to 92, because every variable is related to the others. Nonetheless, we found about an 18-measure retrofit package that could save over 3/5 of the water heating electricity at an average cost below 1/10 today's average US household electricity price. Much of that work actually remains undone, although standards and innovation have done part of the job. The supply side could also displace the remaining use cost effectively, but that menu is now larger and worth doing, not just to save electricity, but also to help get buildings off natural gas with their carbon and methane emissions. Now, water heating is one of the more interesting uses for beneficial electrification, and also it offers enormous grid control thermal storage opportunities. You know, it's now pretty common to heat or preheat water by desuperheating air conditioners or by a simple exhaust air heat pump, using, for example, restaurant kitchen exhaust air to heat water for dishwashing. In the Davis house you saw earlier, we heated the water with waste heat from the refrigerator freezer. And now home air to water heat pumps are widely on the market. Their coefficient of performance, COP, measures how much water heating they do per unit of electricity. And a few years ago, 2019-20, the Energy Star best models could produce 40 Celsius water from 8 Celsius air with a COP of 3.5, from -8 Celsius air at 2.4, and from -15 Celsius air at 2, twice as efficient as a resistive water heater. Now, RMI's Innovation Center starts not with cold outside air, but with the warm inside air produced by waste heat from the photovoltaic inverters and IT equipment. So a commercial model can cool the closed equipment room down from 25 or 30 Celsius by heating 15-degree cold water to 40 with a COP around 5 or 6. That exceeds the reciprocal of the efficiency of a good photovoltaic module. So after you adjust for system losses, you can actually make more hot water from a square meter on the roof of photovoltaics running such a heat pump than from a square meter of high-quality solar thermal collector. Now, the Swiss technology shown here is substantially more efficient. The one on the left actually is on the market in Switzerland. It can do up to COP, well, the one on the right can do COP 12.3, that's the commercial unit. If you start with water 10 Celsius cooler than you need, you could get that easily from appliance waste heat or a gray water heat exchanger, or a simple passive collector on a cloudy day. So that's now on the market, as shown in the lower right. It should soon inspire US products, but perhaps a miniature, super efficient high-speed compressor like the one at the upper left, 61% of Carnot efficiency, could even become retrofittable. And notice a low lift water heating like that, warming the water by anywhere from 31 to 13 Celsius, could give you COPs from 6 to 15. Wow. Now, a bigger challenge, probably the toughest part of getting US households off gas, is cooking. Many customers love cooking with gas, or at least actors playing customers say they do. And they say they couldn't cook without it because they're comparing it with awful old electric ring cookers. The common retrofit prescription is therefore induction cooking, which is fairly expensive, not very transparent, somewhat controllable, somewhat efficient, a bit buzzy, usable only with ferrous-bottomed cookware, and potentially risky if you wear a heart pacemaker. However, in Basel, the Croatian engineer Dusko Marovic has developed a conductive, not inductive, cooking system that is much superior to induction or gas because it's designed as a whole system. He discovered that when you heat a pot, the bottom tries to expand, but it can't because it's constrained by the side, so it warps, and that cuts the contact area between the pot and the hob heating it down to just 3 little points, so the heat transfer falls by 2/3. So we fix this with innovations to keep the bottom flat and in full contact at all times. The heat comes from a silicon nitride hob insulated beneath and heated on the underside by brief 2 or 3 kilowatt electrical pulses into resistive coatings. On top is a stainless steel pot whose bottom is conductive, but whose sides and lid are evacuated to 1 millibar. The sensors, software, direct digital controls indicate, program, and set the exact temperature and time that you want for each hob. You can also fry directly on the hob, teppanyaki style if you want. So I've been using the 1st generation version for 12 years. I hope to upgrade it to 5th generation. And the system is superior in all respects, in my view, and it saves lots of money, CO2 and methane, plus the need to renew old and increasingly leaky gas infrastructure. The governor of New York has just backed banning new gas installations in that state, and this could be a pattern. Now, recent tests, including by an independent lab for the California Energy Commission, confirmed that Marovic system is about 2 to 4.5 times more efficient than standard induction cooking, depending on the task and duration, even more if you're cooking for longer, a long simmer. I think this conduction system is exceptional, and the top German-speaking TV chef agrees with that. It does everything but wok cooking, which is easy in a separate electric wok. So just using those vacuum pots also at least doubles induction cooktops efficiency. The pots lose so little heat that when you're simmering, each hob runs only about 1 second out of 50 or 60 seconds. And the power managed electronics driving the hobs heat only 1 hob at a time. The bigger hobs use 2.5 or at most 3 kilowatts. So the cooktop needs only a standard US household 117 volt 30 amp circuit. So full-sized bi-radiant oven, that's a thing from the 70s, not yet in production, could be designed to run on an identical circuit, maybe even on the same circuit, since some designs use 2 elements in the oven of just a few hundred watts each. So that means retrofitting off gas, you wouldn't need 240 volt rewiring. That should simplify the retrofits. Bi-radiant ovens therefore need reassessment from the modern perspective of peak power draw, not just energy. Another business opportunity. They're all over the place. What about the innumerable information technology gadgets swarming over our homes and lives? Grubler et al. Point out that digital convergence enables a single smartphone using 5 watts to operate, 2.5 in standby, to replace upwards of 15 devices, saving electricity by close to 100-fold in operation and 30-fold in standby. But wait a minute, doesn't the smartphone use as much electricity as 1 or 2 refrigerators, as some professional liars keep claiming? Well, no, they overstated this direct and indirect usage by over 2,000-fold, as John Koomey has repeatedly shown. The coal industry keeps pushing this false narrative anyway. Major media keep sensationally reprinting it, so it's widely believed even by some secretaries of energy. As Brandolini's law says, the amount of energy needed to refute BS is an order of magnitude bigger than to produce it. Actually, the International Energy Agency says data centers and global networking equipment in 2014 each used about 1% of the world's electricity, and data centers usage is about flat, thanks to efficiency gains averaging about 20% a year, 2010 to 18. So data centers still use the same 1% of global electricity they used to. Bitcoin mining uses on the order of 0.1% of the world's electricity, maybe a little more now, but not, as a recent Newsweek headline claimed, so much that is, they said, on track to consume all the world's energy by 2020. For details, see the latest edition of John Koomey's his wonderful text called Turning Numbers into Knowledge, and his team's 28 Feb 2020 science article, which we will revisit in Lecture 6. But the energy implications of information technology are actually a lot more complex and more interesting than just what the servers and devices use. Joe Rome showed in 2000 that IT can save enormous amounts of energy, not just by making processes and equipment more efficient, but by reshaping commerce, turning, as he put it, buildings into websites, warehouses into supply chain software, trucks into fiber optics, paper and CDs into electrons. He did a Grist article that said Amazon.com uses just 1/16 the energy to operate its buildings that a traditional bookseller uses. That's when it was a bookseller. And shipping a 10-pound package by overnight air to your home, the most energy-intensive delivery, uses 40% less fuel than the average round-trip drive to the mall. Ground shipping by truck uses 1/10 the energy of a trip by car to the store. In fact, each minute, he said, spent driving to the mall uses more than 20 times the energy of a minute spent shopping on the internet. In the 2 decades since, e-commerce has indeed evolved pretty much as he said, and Joe was not assuming the several-fold more efficient data centers and vehicles develop meanwhile with more efficiency to come. So now that we've seen how to make building envelopes and equipment amazingly efficient, let me end with a few examples of how design integration can extend far outside the building, produce major new forms of value, and make buildings a little short of magical. A standard big box stores or shopping mall's parking lot is paved with dark asphalt. Its radiant heat and hot air roast the store, the cars, the customers, and soak up light, so ever brighter lighting is installed to provide security at night, light that then becomes so dazzling customers are temporarily blinded as they drive off the lot, so they have a collision and the owner gets sued anyway. What would an integrative designer do? Probably use light-colored paving. It cools the store, the cars, the customers. It lasts longer because it's cooler. It reflects light better for night security and for saved lighting fixtures and energy. And it can even have a pervious surface, soaking up water to shrink or eliminate costly stormwater infrastructure. Light-colored paving is also synergistic with the outdoor lighting revolution. That's not only about the now familiar replacement of high-intensity discharge lamps with LEDs. Being tiny little point sources of intense light, LEDs permit advanced luminaire optics with a small aimed mirror at each emitter, creating a seamless checkerboard of extraordinarily efficient, effective, and attractive visibility. Although, actually, I've heard that this model, which was the best a few years ago, may already have been surpassed, certainly a lively field. These are, by the way, stealth luminaires. That is, they light at such an angle that they're above your normal cone of vision, so you don't see them, just their effect on your surroundings. And light-colored paving can reduce the parking lot lighting to as little as 1/10 of a watt per square meter, or about 2% of the ASHRAE norm, with much better visibility and no dangerous dazzling of drivers. Now, here you can directly compare low-pressure sodium street lamps, the yellow at the far end of the street, with super efficient white LED replacements in the front, photographed halfway through a retrofit in Los Angeles. Benefits multiply as we expand the system boundary. For example, in New York City, Mayor Bloomberg and Al Gore promoted white roofs on old and new buildings. In very round numbers, 100 square meters of white roof has a similar climate effect to taking 10 tons a year of CO2 out of the air. Just like an urban tree cools the city about as well as 9 window air conditioners, which of course cool the indoors by heating the outdoors, not to mention more heat at the power plant. Berkeley Lab has shown that replacing dark colored with light colored roofs and pavements, plus shade trees and vegetation, can bounce solar heat away so well that their widespread adoption could cool Los Angeles by about 4 Celsius degrees, cutting the city's cooling loads by about 20%, in addition to any savings from making the buildings and their cooling systems more efficient. Since the photochemical reactions that cause smog double in speed for each 10 Celsius degrees of air temperature, that cooler air, ambient air, would also cut smog by about 12%, improving public health. Just in Los Angeles, the total indirect savings would be worth $500 million a year or so. Berkeley Lab's database lets designers pick paints, shingles, coatings that reject solar heat, but are various pastel colors if you want, rather than white. Another important point is how buildings affect neighbors. Saito Sensei measured around Shinjuku in downtown Tokyo that on a hot, that was a 37.2 Celsius degree summer day, a bystander would receive a radiant flux of about 800 watts, enough to kill you over some hours. And only about 150 watts of it was directly from the sun. The rest was reflected from or radiated by adjacent buildings and pavement. The average anthropogenic heat addition in that area was nearly 4 times the net insolation. So urban heat island phenomena are important not just to energy, but also to basic health and survival. Where else can we extend energy and resource efficiency beyond the building? Well, there are 6 reasons developers put pipes and wires in the ground to connect new housing to remote infrastructure: telecoms, electricity, cooking fuel, potable wire, sanitation, and stormwater management. Yet today we have comparable or better on-site solutions for each of those needs. Net zero buildings, although eliminating wires means you can't have net positive buildings selling back to the grid. Wireless telecoms, all electric cooking, solar thermal with thermal storage works well too. Rainwater capture and gray water reuse with water efficiency, landscape-based stormwater management, and on-site sanitation. And if we combined all 6, guess what? We would no longer need to bury pipes and wires, like throwing money in a trench and covering it up. Developers would gain better siting and phasing flexibility. They'd have better cash flow. Occupants might pay a little more for on-site maintenance, but they would pay far less for the decades-long burdens of the costly remote systems, public bonding, the pipes and wires in between. Societal resilience would rise. Societal costs would almost certainly fall. And there's some anecdotal evidence suggesting the developer's capital cost may fall too. So this seems an idea well worth trying. But to get the box, the little ticky-tacky out of the box, we have to remember there's no box. On the east side of Pittsburgh, combined storm and sanitary sewers overflowed with heavy rainfall, backing up sewage into streets and rivers. We've likely seen this in a lot of places. So that's a $1 trillion national problem called combined sewer overflow. RMI was asked years ago to find a better solution than digging up the whole area to separate the pipes. Civil engineers, bless their hearts, often think of water as cubic meters of nuisance to be removed rapidly to someplace else in large concrete pipes. So instead, 23 years ago, RMI's design charrette convened landscape architects and real estate developers, and their graphics-rich solutions in the book on the left, $1.2 billion cheaper, needed no new pipes, but would turn the landscape into a beautiful wildlife-rich sponge. The Army Corps of Engineers launched the largest urban stream restoration in the US with wetlands and native plantings, augmented by a vibrant watershed association that sells rain barrels, installs rain gardens, helps homeowners connect their downspouts to the right destinations, and keeps reducing impervious surfaces. So in 2018, the mayor's capital budget funded the final design for the rest of the green infrastructure. It's a good archetype for solving this $1 trillion problem nationwide and well beyond. incidentally saving a lot of cement, to which we'll return in the industry context lecture number 4. Remember how people shopped longer and bought more food in the beautifully daylit supermarket in Foxborough? Well, that's the tip of a very lucrative iceberg. The measurable side benefits of energy efficiency are often 1 and sometimes 2 orders of magnitude, factors of 10, more valuable than the saved energy. Bill Browning and Joe Rome discovered this in 1994, about 20 meters behind me, and they first reported it in this set of case studies published with DOE. Their thesis soon became a major new field of study and action. The side benefits they found had previously been dismissed as ignorantly overlooking what business schools taught as the Hawthorne effect, supposedly showing that productivity gains came not from improving workers' conditions, but just from paying attention to workers. Bill and Joe, however, found important drops in error rates in postal service mail sorting when lighting quality improved. So they started looking. They quickly found many other convincing examples. And finally, they discovered that the Hawthorne effect, though still widely taught, is an urban myth. What was actually measured was meaningless. It certainly did not support the thesis carelessly extracted from it and still being taught in leading business schools to new generations of managers who will therefore miss these opportunities. Ask me later if you want to know more about that, or look up Hawthorne effect in Wikipedia. There's been a good debunking over the past decade. Now, here are 8 classes of effects that were quickly discovered once Bill and Joe realized that they could look beyond the myth and just analyze real data. Some of these became exhaustively documented. For example, Roger Ulrich combined thousands of peer-reviewed papers showing better clinical outcomes in green and efficient healthcare facilities. So now any responsible owner will design that way to improve care and save money. I'll illustrate just a few of these effects. Some are subtle but valuable. For example, in supermarkets, optically super efficient LED lighting and good lighting design turned out to reduce the energy trapped beneath the plastic wrap of refrigerated meats and other perishable foods. So that reduced the refrigeration required to keep them cold enough for safety, and it increased their freshness and shelf life. That's worth a lot. For a cutthroat business with margins around 1%, big deal. But let's try a more mundane example in the most important kind of commercial building. A typical US office nowadays pays over 200 times more for people than for energy. Good efficient office design is widely observed to make people about 6 to 16% more productive. So that's about 10 to 30 times more valuable to the bottom line than eliminating the entire energy bill. Some firms don't even bother anymore to calculate the economics of efficient design. They'll just do it, confident that even a small fraction of the expected gains in labor productivity will pay for it regardless. We've had clients who, when they experience the visual, thermal, and acoustic comfort of a super efficient office, simply say, "We got to have this." And then they're startled to learn there's thick icing on their cake. Their energy bills are going to go down too. So energy efficient retrofitters should focus on what their customers want, which may have little or nothing to do with energy. Energy is a small cost for most. They may care much more about the productivity, health, and happiness of the people, like the retention of the people who are their biggest operating cost. A few old but instructive examples. In this big building where 2,700 staff prepared engineering drawings, designs, and for airplanes, this early daylighting design saved 3/4 of the lighting energy and half the total energy with, in those days, a $2 million extra cost. Nowadays, daylighting would probably reduce net construction cost. And they expected a 4-year payback, but 15% lower absenteeism and 15% higher productivity, both traced to the daylighting, cut the payback to 1 year. And then the lower overheads enabled Lockheed to win a big contract whose profits paid for the whole building. Realizing the building was an important source of competitive advantage, Lockheed stopped talking about it. Too late. This simple story of helping workers feel better and see what they're doing could be replicated throughout industry. Even in sophisticated places like auto assembly plants, I often find a complete absence of lighting design. For example, cars move down the assembly line beneath 6-foot long angled fluorescent overhead tubes. So you're either on this side shading your own work, looking into glare off the sheet metal or looking into the other lamp. Just pointing the tubes up toward a white tent enormously reduces fatigue and improves ability to work efficiently and spot defects. The lighting wizard, Nancy Clanton, seeing the same opportunity in an electronics plant, simply draped a bed sheet above the workbench, pointed the lamp upward, and listened to the workers who were gasping, "Hey, now I can see what I'm doing." Walmart ran out of budget on a building project, and they could daylight only half of this experimental store. All their sales terminals, though, were hardwired to Bentonville, where somebody noticed much higher retail sales pressure on the daylit side of the building. They swapped merchandise around and confirmed the cause was the daylighting. Managers also reported that workers preferred to work on the daylit side. That lesson soon got widely applied. Indeed, a respected research firm surveying a West Coast retail chain confirmed 40% higher retail sales per square meter and year in well daylit shops after controlling for other variables. What does that do for your margin? Big side benefits have also been documented in industrial production, not just manufacturing, but even sectors like steelmaking, where they can double energy efficiencies, savings, and financial returns. You'd think every industrialist would be all over this, but few are. Another business opportunity. The moral of this story is that saving energy is often just the first taste of a cornucopia of even more valuable benefits. Don't ignore them. For many customers, start with them. Finally, with thanks for your stamina, let's end with 5 slides to emphasize that superlative energy efficiency can accompany other very valuable attributes and is best integrated with them. Sometimes the right client and the right designer meet with magical results. In 1978, the late Ton Alberts was hired to design a new bank headquarters in the district where the 3,000 employees wanted it in South Amsterdam. In a brave and brilliant stroke, the bank's directors hired Ton, a residential architect, because he had never before designed a commercial building, so he would have beginner's mind. The directors gave Ton a simple brief. They demanded an organic building full of happy people, art, natural materials, sunlight, green plants, energy efficiency, low noise levels, and water, and it shall not cost 1 guilder more per square meter. They got this extraordinary 50,000 square meter anthroposophic building, Rudolf Steiner style with no right angles, and it soon became the best known building in the Netherlands except the parliament, and it helped what was then NMB Bank, later ENK, soar from number 4 to number 2 among the Dutch banks. In these interiors, the image isn't crooked, the columns are crooked. This takes skilled builders, carefully supervised. The building initially used 1/10 the energy per square meter of ENG's previous facility, or 1/4 the energy of a bank headquarters built by a competitor next door. It was so quiet that to bring in sound and humidity, they used cast bronze flow form sculptures in the handrails in the circulation spaces. So this is a stream splashing and gurgling down the handrail, and occasionally it breaks loose and drops down to the next floor in a little waterfall. Bankers in 3-piece suits have been seen playing in the handrail. So including fixtures, furnishings, and equipment, the building cost right around the Dutch market average, and it hugely boosted the bank's productivity, reputation, and effectiveness. The virtual tour of my house that you just saw ends by discussing biophilia and the wonderful terrapinbg.com publications about it, starting with 14 patterns of biophilic design. And now there's a wonderful new book called Nature Inside that I commend to your attention. Many people report feeling better after they spend a while in my home. The video tour you saw helps you see why. We're currently ripening, banana crops 79 and 80. The iguanas, snakes, African pygmy hedgehog, and singing frog have all unfortunately died of old age, and I've been too busy to replace them. However, you may notice some friendly fish, along with our meditative family of orangutans, which fortunately have not yet learned spearfishing like this wild orange friend in Borneo at the upper right. But at least if you fall in the pond, maybe you can get a helping hand out. To do all this, we just need some gifted designers to give us a Vulcan mind meld, perhaps designers with 4 thumbs per brain and whose engineering skills in crafting from minimal materials the strong and secure treetop nests they build each night have been praised in the proceedings of the National Academy of Sciences. And so we end where we began, learning to build ever better nests, and I hope getting confused on a higher level. Thank you.